Welcome to my presentation. I'm going to cover what symmetric encryption is and how it differs from other encryption types. And finally, I will be going a little deeper into modern algorithms and best practices today. So, first of all, what is encryption? Encryption actually goes all the way back to ancient times. It refers to confidentiality in our CIA triad, and to put it simple, it's about keeping something a secret so that only the people intended can read and understand it. We do that today by encrypting a plain text to some ciphertext using a key and then back again. To sum it up, encryption is two-way, the opposite of hashing. This is, we use a key to encrypt and to decrypt. So why is this important? Well, it is because the majority of online communication today takes place over an insecure network, the internet, where we send sensitive data. And lastly, it makes no sense to talk about symmetric without mentioning the other encryption types. Symmetric is where we use a shared secret key. Asymmetric is where we use two keys, a public and a private. And finally, hybrid, where we combine both and exchange our symmetric key by using asymmetric encryption. TLS is a great example of hybrid, and we use this widely in HTTPS because asymmetric encryption is mathematically heavy and thereby very slow. So once the key is exchanged safely from asymmetric encryption, we switch back to symmetric encryption, which is much faster. Well, encryption started somewhere with the classical symmetric types. The first symmetric encryption introduced was the Caesar cipher, which is very basic. It works this way if we have a plain text character of A that we want to encrypt and we have a key of the number 3. Then we move the character A 3 places forward in the alphabet, so the plain text A becomes D in ciphertext, and so on. The genera is also pretty simple and can't really be used in reality, but I'm gonna quickly introduce it. It works by taking a letter A, which is the first letter in the alphabet. And then we have a key, could be the letter D, which is the fourth letter in the alphabet. We add the numbers 1 plus 4 and get 5, so our ciphertext would be the character E because it's the fifth letter in the alphabet. Pretty simple, right? OTP is short for one-time pad. It's said to be unbreakable, but cannot be used in reality either, because the plain text and key must be the same length. And the key can only be used once and must be truly random, for example from air turbulence, lava lamps or waves on a beach. That said, OTP is still usable in some login form, but cannot be used for encrypting larger things, for example, chat communication. OTP is used practically by soaring bitwise, where we use a truth table. We soar our key with our plaintext and thereby get our ciphertext. So, this slide summarizes the encryption types we use today. We operate with two different types, block ciphers and stream ciphers, and I will cover the most known ones. Block ciphers encrypts data in fixed size blocks. Basically, we encrypt a block or chunk of plaintext at a time using our key to transform the plaintext into the ciphertext. If a block is not filled, then we pad the rest by doing rounds of operations. So we do not use SOAR, also called the truth table, but instead we encrypt many blocks with one key. The most famous block ciphers are AES. We have a term called modes of operation. This is used when we encrypt a plaintext that is larger than one block, so we need a method for that. We have different modes of operations where some are secure and some are not. The first one is ECB, which is not secure as it creates identical blocks. I had an assignment once where we encrypted an image using ECB, and although the image was blurry, you could still see what it represented. CBD is slightly more secure and uses an initialization vector sent in plain text, but it does not provide integrity. Then we have GCM, which is secure. It provides authentication and integrity using hashing. It also uses an initialization vector, and we have a counter that counts up from block to block, which makes it random. In stream ciphers, we encrypt data 1 bit or 1 byte at a time. No padding or modes of operations are used, so it simply generates a key stream and saw the plain text and the key to get our ciphertext. They are often used because of their speed and simplicity. The most known ones are Salsa 20 and Cha-Cha 20, which uses a nonce. Then we have RC4, which is fast but very simple and only swaps bits and thereby is insecure. Also we have Web, which are used in Wi-Fi, but it's completely broken and can easily be cracked with aircrack. So what are the best practices? Well, no doubt about it, we should be using AES. The best version would be AES 256 GCM, which is classified by the NSA as top secret encryption. AES are great because the original key generates new keys, which are called round keys, and a key schedule is used. Round keys are generated over many rounds, where each round makes it harder to break the encryption. AES 256 uses 14 rounds. So basically, to break AES, one would have to try combination by raising 2 to 256. Yeah, you do the math, but it would take years. The only thing about symmetric encryption is that we need a safe way to exchange the encryption key before we can use it. And that's where asymmetric encryption comes to play, which I will cover in my next presentation. Any questions?